Hi, this is Greg Abston from the Laser Training Institute of Professional Medical Education Association. Welcome to our short video series on medical laser training. In this laser service video, Keith Steckow will be giving us an introduction and orientation to a very complex system, the frequency doubled into YAG laser, also known as a KTP laser. The point of the discussion is to introduce service people to some of the complexities of multiple beam pathway lasers with frequency doubling crystals and Q switches. Of course, you'd need a specific service manual to do this service, but here you can get a better idea of what all is involved with this. Keith is one of the senior faculty for our Laser Training Institute and has been in the laser field for over 45 years. If you have technical issues with most any type of laser, Keith is a person to call. It's important to remind you that these short videos are not intended to enable you to perform service on systems like this. These videos are incorporated into our other more extensive laser training, and here it's intended just to share an overview of the subject with you. The Class 3B and 4 lasers in these systems and the potentially lethal power supplies involved can present serious hazards for those who have not received proper training beyond these short videos. We teach entry-level laser repair classes in our quarterly week-long courses. This short video is not a training video on how to work on a LaserScope KTP laser, although we use that laser as an example. It's a general orientation to similarly complex laser systems so that you are introduced to optical decks with multiple beam pathways and inclusion of frequency doubling crystals and Q switches.
My name is Keith Steckow. I am a senior faculty at the Laser Training Institute, and I'm here today to introduce the refrigerator that may have been sitting in the back closet of your OR. It's called a KTP laser, and it has a 532 nanometer wavelength and 1064 fiber delivered, and I'm here to kind of explain a little bit on my process of evaluating the outputs and how to troubleshoot. I've opened up the top cover and removed the shield and to expose the laser deck. And this is a lot to encompass here, but we have a neodymium YAG rod here. It's flash lamp pumped. Gets about 35 amps of current through the flash lamp, and it produces up to 100 watts of neodymium YAG and 40 watts of frequency doubled YAG 532. It's really broken up into two stages. There's the primary, the laser itself. Over on this side, that's the first train. We'll call that the first train alignment, and the second train alignment is where it's conditioned and comes over. All the power is measured by the detectors, and it's focused into two separate ports. One for a microbeam, so you can do stapedectomies, things like that. It's a small micromanipulator. And the other one where you can use an endostat or a fiber optic delivered energy. The beam passes as follows. This is a Z-fold laser. Okay, so the beam path would go in this direction with a total reflector here, a reflector here. In between these two is the KTP crystal. There is an output coupler and a relay. This device here is the Q switch, and then there's a solenoid for selecting either the KTP side or the YAG side. So it just has a separate output coupler for YAG. And then for lower energies,
Your other hand out of the way.
For lower energies, there's an aperture. So we have a beam select and an aperture here, and then the total reflector here. When operating in YAG, the neodymium YAG, there's a selector relay here that takes the beam path and moves it to a secondary output coupler. These detectors are identical in the fact that the way you adjust them is the same, although they're looking at different wavelengths. And there's a main detector and a safety detector for each wavelength. There's a main detector and a safety detector for the KTP. There's an aim detector. So each of these detectors has to be adjusted for both zero and gain. So the way we zero these is you come up with a DVM and you use TP3 as a ground, and we're looking at millivolts here. So I go TP3 ground and TP1 as the positive on your DVM with no energy entered into it. You zero that out for 0 volts with VR3. Okay, then you move your positive of the DVM to TP2 and use the VR2 to zero that out. And then when you get energy through it, you verify the amount of energy coming out and you make that adjustment with VR4 so it matches the actual energy. It's the same for all of these detectors. Output coupler. That secondary output coupler then acts as the feedback for the head and produces about 100 watts depending on the current in the lamp. The first thing it does is it hits a prism. I don't know if you can see that prism in here. Okay, and that does two things. It steers the beam towards this collimator. Also, a small portion of it is released out of the back of the prism into this detector assembly, and this would be your surgical detector. This is the main detector. And after the collimator, it hits this double prism, turns it right back around 180 degrees, comes through these series of shutters. Okay, there is a beam stop, a safety shutter, a cal shutter, and another dual purpose shutter here. This will open up and let the red aiming beam come through and the YAG come through this pinhole here. Now this is a very important part of this. It looks like just a hole, but what it does is it sets up alignment. The primary angle of attack into the focusing lens. So it comes up through here, hits this prism, and then hits this beam combiner. Now this is a beam combiner for the aiming beam, which has its own collimator, and the YAG beam. So they call this the 633 1064 turning mirror and beam combiner. And then that goes into the fiber launch. Okay. There is also a series of shutter driver boards. So each shutter has a shutter driver attached to it, which is driven from the logic board by these cables here. And just be careful because you can swap these and it'll run the wrong shutter. Experience. So on the bottom side of the shutter are these detectors to detect when it's open and closed. And some of these are dual shutters. It'll work for one side and the other. So it'll open up, it's a dual purpose. There's two of them specifically here. This one has a light valve for controlling the aiming beam of the 532 nanometer wavelengths. So when you're adjusting for a certain level of aiming beam, this will increase the voltage, which decreases the actual energy coming through it. And this is an identical one over here for the YAG. There's no actual, they're not going to put a quarter wave plate or a way of diminishing that energy. They use a light valve in order to do that. Here's the controller board that controls all the shutters and the operations of the laser. There are a myriad of cables. There is a software here that runs the system. depending on the version of the software. They have a dongle that you can access the service software that's in here, or in this case, the service software was on this version of the chip, so I can access service mode here by pushing this little S3 button. Let's turn the laser on. I'm going to throw the circuit breaker in the back, and you may hear a nice hum. And turn the key switch on, and you'll hear a series of clicks where it moves the shutters and the beam selector switch to make sure that it knows what position it's in. Okay. The laser is going to go through a 6-minute warm-up where it tests powers, shutters, and the detectors before coming up in operator mode. You can enter service mode and interrupt the normal startup by pressing S3. If we come back to the display, you'll notice that there's a menu. So that corresponds with each of the buttons here on the front panel. Surgical up is lasers, the on, off, and the interlocks. Surgical down is the KTP laser, current curve. And I'm going to come over here and look at the shutters, and that is going to be lasers, shutters, and detectors is the aim up. So I push aim up, and then you'll get this sub-menu. Okay. Now we can control. Did I get the right one? This is lasers, shutters, and detectors. Okay. Here is a list of the shutters. There's a surgical up, which is the KTP safety shutter. Surgical down is the exposure shutter. Aim up is the pre-aim shutter, and repeat would be the aperture shutter. So this safety shutter will not open unless you have a delivery device in the port. So it knows that there's something connected. I created a little cheater here. It's inserted with the arrow directly up and locks into place. Now that will allow me to open the safety shutter. Do it again. Each of the shutters has a display here for the drive and the actual confirmation from the photocells that says the shutter is actually open. So when I open this, you'll see the drive turns there, and then the switch for the shutter acknowledges that it's in the open position. So when I press the surgical up button, you'll notice that the shutter comes up, the blade comes out of the way, and the driver board sends a signal back through the cable to logic board, and it's acknowledged on the display that it is in the open position. And that happens with all of these shutters. That again? Mm-hmm. And the other one here, which allows the treatment beam out. Safety glasses should be worn during this. In this mode, we were able to calibrate the main and the safety shutters to be identical, so it knows that there's no problems with the laser. This is the beam select switch that switches between ND-YAG and 532 nanometer wavelengths. When the beam select switch is pushed, several things happen. The beam is diverted from the second train to use the ND-YAG output coupler. So there's a solenoid that comes down here and a solenoid that pushes a little mirror in place, so the beam now exits without going through the KTP crystal or the Q switch. This device here, this optic here, is a total reflector. It's what we would call 100% reflective. It's actually about 99 and change percent reflective. There's no adjustment, it's pinned. So, but there you'll notice that there's a little beam stop in the back. This can be removed and a power meter put back here, so we can make adjustments and peak the output of the laser. Well, for ND-YAG first. So next is the laser head. There's no adjustments here. Then there's the beam's aperture, and so when you want lower powers, it has to fire the laser beam through a smaller aperture, and that goes in and out of the way. There is an adjustment for that because it's just a pinhole. Just by loosening this nut and adjusting this Allen adjustment here, you can make sure that the hole is in the proper place in the center of the beam. The next thing it goes by is, of course, the beam select mirror, and this in KTP mode is out of the way. Then we have the Q switch assembly. The Q switch is driven by a Q switch driver down in the console itself. It runs at 25,000 kilohertz, 25,000 hertz, and then comes to the output coupler of the laser. It hits the back of the output coupler, which has it's reflective to a certain point, and a little bit of it is bled out the front to keep the lasing stimulation going. And then it comes back from the long arm here to this relay mirror, and then the short arm here going through the KTP crystal. And this is the adjustment that you need to maximize the ND-YAG for in the KTP mode. So this will come out, this will come out, this beam stop will come out. You'll put your power meter back behind this because some leaks out, and you will peak that ND-YAG energy on this mirror here. Initially, when you peak the ND-YAG, you are going to have the Q switch and the KTP crystal out of the way. When we insert the KTP crystal, before we do the Q switch, we'd adjust this, the non-Q switched mode maximum out of this laser is about 4 watts. It's only when we enter the Q switch in that we get the higher gain of about 10 times greater on the average when we put the Q switch in, because every time that Q switch starts and stops, you get a spike, and that increases the average power. This adjustment is very touchy. It does angular in both directions, and can easily burn if you go too far off of the center of the crystal. So be careful when adjusting this. And then the Q switch has to be aligned perpendicular to the beam path, and there's a method we call dipping the Q switch, so it has to interrupt as much of the energy as possible. So you want to adjust it for a negative peak. When all that is satisfied, you'll have both beams coming out of the output power, both 1064 and 532. The beams are then split by the prism, come off of this relay mirror, come through a collimating mirror, and as the beams are split, There is a dump for the 1064 and the KTP continues on. After the collimator, there is a quarter wave plate that sets up a polarization. Okay. And you can see as I turn this, some of the beam is allowed to pass through the first plate of the polarizer pair. Okay, and that is dumped by this beam dump. And a portion of it, depending on the angle, goes to the secondary optic of the polarizer pair and gets used as our usable energy. And is picked up by the first detector here, the KTP surgical detector. After the polarizer pair and the the main detector, it comes by and hits these three shutters. This shutter is an aiming valve for the aiming green beam, or they call it a pre-aim shutter. This is the exposure shutter, and then the opaque total beam block, which is the safety shutter itself. Okay, all three of these need to be open in order to make a full exposure. Okay. The next thing it hits is the KTP safety shutter, and then exits into the option of the beam switch. This allows you to use port 2 in the KTP, or in YAG mode, exit the YAG energy out of the endostat coupler. So we have two separate fiber ports, and they're selected with the beam switch.